All right, is this working?
Not yet.
Okay, 1 second. Sorry, I might be having the same issues that Dr. Paul had. Let me just try this. Is this fine? Can you see?
Not yet.
Okay. Sorry about this. Maybe I'll have to do the same thing. Wait, so then you can see this screen. Can you see this now?
Yet.
Aye. All right, perhaps I'll just send you the presentation. Would that work?
Okay. Sure, no problem. Yeah, we had that type of security issues with, there was a guest from Brazil, I think was from Chile. Yeah, from Chile, yeah, he had the same type of problem.
Yeah, I see the option to share the window that's for this presentation, but it doesn't actually show any preview or anything. So.
How you try to share maybe just the a window instead of the whole screen?
Yeah, I am doing the window option, but then it's all grayed out. It's not.
All right. Okay, so let me just download and share your presentation. Okay. All right, can you see the presentation?
Yeah, looks good.
All right. There you go.
Okay, thank you. Thank you for the introduction, and thank you for giving me the opportunity to share my dissertation work. I'm very pleased to have the opportunity. So title of my talk is Core Entropy of Finite Subdivision Rules. This is my dissertation work. If we go to the next slide, I have more or less just a brief skeletal breakdown. So in the introduction, I'll just share a little bit about the story behind this quantity as I see it, or the quantity of main interest that I study in my dissertation. I'll discuss a little bit of preliminaries, just introduce the bare bones machinery and terminology, sufficient just to be able to walk through the main result, talk about the main result and what it rests on, and then a little bit about one of the main, I guess, applications, you can call it, of the main result. So let's see next. Okay, so setting is complex dynamical systems. In this setting, you have a Riemann sphere and a rational map, and you're interested in what are called forward orbits. So you take a point for a fixed system. You're thinking about a point in the Riemann sphere and iterating it, or obtaining a sequence of points by iterating this map on this point. And as far as for a fixed system, what understanding orbits could mean, you could be interested in things like limits of limit points of forward orbits. You could be interested in topological and various other properties of the set of all limit points of the forward orbits. And you could, wondering maybe go backwards. How does the set of iterated pre-images distribute themselves in the Riemann sphere? A lot of things have been done in this setting in the 20th, 21st century. The particular question of interest to me is for instead of for a fixed system, for let's say a couple of systems or pair systems, how could you maybe compare the complexity or how complicated the orbits are for one system compared to the other? So that's the main question of interest. So if we move on for next slide. Okay, so how does one then go about measuring this complexity or quantifying how complicated the set of orbits is? And it's a bit tricky to do if you were to try to establish a way to simply categorize or count the orbits directly. So instead, what you try to do is you measure the rate at which the number of distinguishable partial orbits grows. So because you have the luxury of a metric in the setting, you do the following thing. So you fix a resolution, which is to say you fix some positive epsilon, and you define a new metric on this space where you say the distance between 2 points is the minimum of the distance between its iterates up to, say, an iteration. So that defines a metric dependent on some value n. And then you consider maybe covers of this space, like the Riemann sphere, by metric balls under this d sub n metric, if you'd like to call it that. And then the compactness of the space gives you a minimum cardinality of such covers. And this is corresponding to the, let's see, max cardinality of a set of orbits of your function, such that no two are within epsilon of each other. And you consider the growth rate of these sort of distinguishable orbits as epsilon goes to 0 and as n goes to infinity. So as you take, so that's the idea as far as how you quantify the complexity between orbits. So let's go to the next. So this is called topological entropy, this quantity. And yeah, so let's go to the next slide. Okay, so in the setting of complex dynamical systems, topological entropy, there's a result by Mikhail Lubitsch circa 1982 that says if you have a rational function that's non-constant, its topological entropy, the quantity defined on the previous slide, is just the log of the degree of the function. So, as far as what's behind this, there was a result of Mizurovich and Pritsitiki that showed that the topological entropy is at least as big as the log of the degree, and Lubitsch in this result in 1982 shows the reverse direction. And so the conclusion is that ostensibly topological entropy is not particularly interesting in the setting of complex dynamical systems, because let's say you just take degree 2, all the maps with varying dynamical behavior just have this one quantity log 2 that characterizes how complex they are. So okay, so next slide. Okay, so there's still hope for entropy being something usable in this setting to help you understand how complicated complex dynamical systems are. And the story sort of starts with work that was done by Milner and Thurston. So the setting of that work is you have some continuous piecewise monotone interval map. And Milner and Thurston, I forget exactly when it was, but they studied the dynamics of such maps. And these, just for some terminology, they call the maximal subintervals on which your function is strictly monotone. They call these laps, and they call the number of such intervals lap numbers. So they start in the quadratic case. So if you move to the next slide, let's say you take a quadratic function of x squared plus c for some real constant c. From that paper on iterative maps of the interval, okay, so it's circa 90, or I'm sorry, 88. You'll have like maybe some quadratic map on the upper left part of this figure that has a lap number of 2 corresponding to these 2 maximal intervals of strictly monotone behavior. And then you consider maybe the lap number of its iterates. So, so you move to the next slide, please. So then you can define what's called a growth number by taking the number of laps of the kth iterate of your function, and take that kth root and take that limiting value, take the limit as k goes to infinity. So Milner and Thurston call this quantity the growth number of your function. And there's a result of Rothschild and Mizurovich and Slank that says that the topological entropy of that continuous piecewise monotone interval map is just the log of this growth number. So, okay, that's fine. So how is this giving us hope for entropy in complex dynamics when you're still just sort of saying that you get log of some growth number? Let's see. So the hope lies in the fact that real polynomials also act on the complex plane as well as in intervals in the real line. So go to the next slide, please. Okay, so for quadratic polynomial with real coefficient c, if you were to have it act on the Riemann sphere, you could look at this one-dimensional subsystem. So since that parameter is real, you'll have the you can look at the intersection between what's called the Phil-Julia set with the real line and consider that map's restriction and apply Milner and Thurston's so-called kneading theory, which is present in the work that was cited above, to this like one-dimensional subset. And then now if you want to step up and say, okay, for complex parameter C, you don't have this preserved one-dimensional subset by just taking this Phil-Julia set and intersecting with R. So then what can you do? Well, in the Phil-Julia set, there exist one-dimensional subsystems called Hubbard trees, and we'll talk. I'll say more about them later, but this is essentially the idea behind this. Okay, so for a special, oh sorry, one second. Yeah, so for a special subsystem of, or sorry, for a special class of quadratic polynomials with complex parameter C, if you look at the field, oh, can you go to the next slide, please? Yeah, so you could parameterize a particular special family of quadratic polynomials by what's called the external angle. I'll talk about that a little bit later, but if you do so, Thurston continued this work and analyzed a notion of entropy associated to this function restricted to this one-dimensional subsystem called that's given by your function's restriction to this one-dimensional tree called the Hubbard tree. I guess I don't need to say one-dimensional, but at any rate, that graph. So if we can go back to that graph, that graph is like a wacky-looking graph, and it's pretty interesting. And for this important class of quadratic polynomials, it's suggesting the idea that maybe entropy is worth studying, or there's some notion of entropy that is salvageable in this setting, I guess. So Thurston called this quantity core entropy. So the topological entropy of your quadratic polynomial's restriction to its Hubbard tree is called the core entropy. Okay, so next slide, please. Okay, so say a little bit about finite subdivision rules. This is so I won't say that. So finite subdivision rules is so I'll only talk about them as it pertains to complex dynamics, but the theory is much more general. But the idea is that you tile the Riemann sphere with finitely many tiles, and that's tantamount to equipping the Riemann sphere with a finite CW structure. And this is what you call your subdivision complex, and we typically denote it S sub R. Okay, so then you take such a structure and you look at the pre-image structure. So you take each of the cells and you take its pre-image and you say, if each cell is contained in a cell of that subdivision complex S sub R, then that pre-image CW structure is said to be a subdivision of the subdivision complex. Right? So with respect to these cell structures, provided that you have this subdivision, rational maps are then cellular, which means that they take K-skeletons to K-skeletons, and the map is then regarded as a so-called subdivision map. Okay, so this is what I'll mean when I say I am realizing a function or a quadratic map as a subdivision map. It means that I've, I don't know, modeled this thing using the structure of a finite subdivision rule. Okay, so next slide, please. So natural question is to ask, what reason is there to use finite subdivision rules in complex dynamical systems? Well, there's work done that's done, I think, separately by Bonkenmeyer and then Cannon, Floyd, and Perry and Kenyon that say for a post-critically finite map, a post-critically finite meaning that the forward orbit of its critical point is a finite set. So for such a map with no periodic critical points, sufficiently large iterates of the map are realizable as subdivision maps of finite subdivision rules. So they exist in abundance, and so they have a place in this setting. Next slide, please. Okay, so so then, as far as they may exist in an abundance, so how do you typically construct these finite subdivision rules realizing your map? Well, for the specific case of quadratic polynomials, in particular, certain quadratic polynomials that I'll specify soon, you look at. Sorry, one second. I'm a little. Is this slide the? Can you go to the previous slide, please? Okay, yeah, this is fine. Can you move on to the next slide, please? Okay, so if you take an example from the quadratic polynomial z squared plus I. Is everything okay?
Yeah, you can continue.
Okay, sorry. So for this particular example, z squared plus I, what's depicted in the figure above is like an image of its filled Julia set, or at least part of its filled Julia set. What you've done is look. This is like a depiction of its Hubbard tree, or I mean, roughly speaking, and so what you could do is equip this subset of the filled Julia set by with a tree structure by taking branch points, in other words, points that decompose the tree into at least 3 pieces, and post-critical points. Mark them as designate them as vertices, and then all of the arcs that connect them within this tree are your edges, and then you could also use what are called external rays, which I'll talk about in a moment. So what you could do is basically look in these filled Julia sets to try to successively build the one skeleton of your subdivision complex. And so next slide, please. So then, cleaned up, it would look maybe something like this. So z squared plus I, if you were to equip the Hubbard tree, or this subset of the filled Julia set with this sort of one skeleton structure, you could take including maybe these rays that go to infinity. The idea is to take your subdivision map, take its restriction to the one skeleton of the subdivision complex, and look at that thing's topological entropy. So there's 2 things that are being named the same thing because in the particular setting of this important class of polynomials called Misiurowicz polynomials, they do coincide, right? So we give it the same name. So this is what we're calling core entropy. So all in all, there's Thurston's core entropy that's just a quadratic polynomial's restriction to its Hubbard tree, the topological entropy of that, and then there's realizing a polynomial by a subdivision map and taking its restriction to the one skeleton, and that's what's also being called core entropy. And we'll justify a little bit of the namesake here in a moment. So if we look at this example, the cell subdivisions are for this, by making this realization, the cell subdivisions will induce edge subdivisions. And what you could do, is encode the edge subdivisions in a matrix called the edge recursion matrix, where the ijth entry of that matrix is the number of cells in the subdivided complex R of SR of type I that are contained in a cell of type J in the subdivided complex. So this might be a little bit complicated. My plan was to kind of going back and forth between the previous slide to kind of demonstrate how this edge recursion matrix would arise in this particular example. But I guess if we could take a look at the next slide, I think it'll probably be sufficient to just like maybe look at this matrix and parse the entries. But so the idea is, like, let's say you were looking at this entry 1, 3 that has 2. The idea is, if you look at that complex above, in the previous slide, one more back. So slide 14, when you look at that subdivided complex, if you were to, you sort of, there's nothing guiding you at the moment as far as like how you should label the edges. But if you just designate labels to the edges, each of these are then having some type of 1 through the number of edges. And then if you look you can make identifications between, because each of the edges in the subdivided complex are contained in edges in the original subdivision complex. You look at each of these edges, you look at their numbers, and you say, okay, what types are they? And correspondingly, when you look at that numbers edge in the original subdivision complex, this would mean that there are, there are 2 cells in the subdivision complex of type 1 that are contained in cell that you'd originally labeled, let's say 3, in the subdivision complex. So if we can go back to slide 16 or 15, I guess. Oh, 16, thanks. All right, so so you can use standard machinery from the theory of symbolic dynamics to demonstrate that the topological entropy of a subdivision map's restriction to its one skeleton is equal to the logarithm of the spectral radius of this edge recursion matrix. So for this particular example, the quantity that you obtain for the entropy is equivalent to, the quantity that you obtain that was originally defined by Thurston to be core entropy. And natural question then is just like, for what maps can you expect such an equivalence? So now I think we'll proceed. Next slide, please, to the main result, or at least the statement of the main result, and then I'll discuss some of the preliminaries to just walk through it. But if you have a Misiurowicz polynomial, these are, okay, so if you have a Misiurowicz polynomial with Julia set J and Fatou set F and Hubbard treat H, I'll just make the statement of the main result, and we'll talk, and I'll introduce the terminology in a moment. But let's see. So say you have a finite subdivision rule realizing your polynomial, and let's say you have SR1 is the one skeleton of the model subdivision complex. You consider that polynomial's restriction to the one skeleton. You consider also, let tau be the map, the polynomial's restriction to the Hubbard tree. So if for each open edge in the subdivision complex, either the edge is completely contained in the Julia set or the edge is completely contained in the Fatou set, then the union of the edges in the Julia set is connected. And the union of the edges in the Julia set is connected. Then the topological entropy of the map's restriction to the one skeleton is the same as the topological entropy of the map's restriction to its Hubbard tree, or the entropy is 0. Right. So, and in particular, if all open edges of the subdivision complex are completely contained in the Fatou set, then the entropy is 0. That's the particular case in which the entropy is 0. And if there's, so if there's an open edge in the subdivision complex that such that your edge is contained in the Julia set, then not only is and that the union of edges in the Julia set is connected, then Thurston's core entropy, defined to be the topological entropy that maps restriction to the tree, is the same as this entropy that we're defining to be just the topological entropy of a subdivision maps restriction to its one skeleton. So in this way, this is somewhat of a generalization, because we'll see in a moment that that the entropy defined as the topological entropy of a maps restriction to of a subdivision maps restriction to its one skeleton can be, you can model other systems that are outside this this original setting with subdivision maps. Okay, next slide, please. Okay, so just quick remarks about terminology. So in the setting, so you have complex dynamics and you're considering quadratic polynomials in particular. So basin of attraction is a set of all points which eventually iterate to infinity. And the field Julia set is the complement of the basin of attraction of infinity. It's typically denoted K of P. And the Julia set is the topological boundary of the field Julia set. Okay, so next slide, please. Okay. So for a set, a subset of the complex plane that's compact, connected, and full has a Riemann map from its complement to the complement of a closed disk of some radius, right? So for each parameter in a circle, like that you could use, that you could represent using R mod Z, this set, which is the pre-image under this Riemann map of a ray with angle T, is what's called an external ray for that compact, connected, and full set of argument or angle T. So I should have a picture coming up in a moment to make this clear. But so when K is locally connected, there's a well-known theorem of Carathéodory that tells us that this map extends continuously to the boundary, and we call the limits of these points as you take the radius to go to whatever the radius of that disk might have been, the landing point of that ray, if that limit exists. So if we look on the next slide, I depict some rays for particular compact connected full sets. So the Mandelbrot set in the complex plane is one such set, and you could define on the complement of the Mandelbrot set this Riemann map that goes to the complement of a disk of some radius. And if you were to think of a ray maybe emanating from the origin and look at its intersection with the complement of that disk of some radius, the pre-image under that Riemann map would correspond to that one ray that looks like it looks like it hits one of these antenna attached to this like top bulb of the Mandelbrot set. And then another setting in which external rays, another set for which you want to think about external rays is field Julia sets for certain polynomials. So here on the right is depicted a field Julia set for a polynomial. And again, you have a compact connected full set, and on its complement you have this Riemann map, and so these would be what these sort of rays look like. So if we go to the next slide. Okay, so Mazurovich polynomials. Okay, so for a complex so Mazurovich polynomials are just complex quadratic polynomials, in particular for which the critical point is eventually periodic. So it may not itself be periodic, but eventually it lands itself in some sort of cycle. Okay, so for such polynomials, the structure of the field Julia set is that of a dendrite. So it's a locally connected continuum that has no simple closed curves. So for instance, the example that I'm using in this presentation of z squared plus I has a filled Julia set that looks like this dendrite here. This, let's see. So next slide, please. Okay, so then what are Hubbard trees? So you're looking at a Misiurowicz polynomial and its Julia set, which coincides with its filled Julia set for Misiurowicz polynomials. Take a finite invariant subset of the Julia set, which is to say, one of these sets that under the map it's going to map to itself. We'll define what's called the convex hull of that set in the of that finite invariant subset of the Julia set in the Julia set. We'll denote it by this square bracket around A. It's going to be defined to be the smallest closed connected subset of the Julia set that contains that set. If you denote the post-critical set, again being the forward orbit of the critical point, which for this quadratic polynomial, if you're just looking at the finite critical point of just 0, if you denote this, let's denote this post-critical set by omega. The Hubbard tree in particular is the convex hull of the post-critical set in the Julia set. So it's the Hubbard tree of a Misiurowicz polynomial, which, I mean, there are Hubbard trees associated with other polynomials, not just Misiurowicz polynomials, but we'll pay special attention to these. The Hubbard tree is the smallest closed connected subset that contains the post-critical set of that polynomial. So you look at the critical point, you look at its forward orbit, it's this finite invariant subset of the Julia set. You look at this smallest closed connected subset that contains it, and then you get this, tree that's contained in your dendritic Julia set for Misiurowicz polynomials. Okay, so next slide, please. Okay, so key propositions that my main result rested on. One is from Adler-Konheim and McAndrew from a paper on topological entropy in general. It says that if you have a compact topological space and a continuous map from that space to itself, and suppose you were to have a decomposition of that space into two closed subsets that were invariant under this continuous map, which is to say, like their images were contained in themselves. Then the topological entropy of that map is just the maximum of the entropies of the maps phi1 and phi2, which are just the restrictions of that continuous map to those closed subsets. So the second proposition due to continuity is if you have a compact metric space and a continuous map from that space to itself, and you have some closed subset of that space that's invariant, and additionally for any point in that space, the distance between the iterates and that closed subset tends to 0 uniformly on compact subsets or on any compact set in the complement of that closed set, then the topological entropy is going to be the same as the topological entropy of the original map phi is going to be the same as the topological entropy of the map's restriction to that closed subset that all these points are iterating towards or converging towards. So those are key propositions on which the main result rests. So we go to the next slide. Okay, so you start with this first observation, which I'll call lemma 1. Say you have a Misiurowicz polynomial map, and let's say you realize it by some finite subdivision rule R. And so let's say you call the model subdivision complex S sub R, and let's say you call its subdivided complex, which is determined by taking preimages of this complex, R of SR. And let's call the Julia set J of this polynomial. Now, if you have an edge of this subdivision complex that is contained in the complement of the Julia set, then that edge cannot properly subdivide. So a lot of what this result rests on is just this conjugacy to between. So as I'd mentioned before, if you have this compact connected full set, you have this Riemann map on the complement to the complement of a disk, right? And using such a Riemann map, you could you could establish a conjugacy between a power map, like z goes to z squared in particular, to whatever Masirovich polynomial you're considering. So every Masirovich polynomial, you can consider this conjugacy. And so a sketch of the idea for this lemma, for the proof of this lemma, is just by contradiction, which is you start by assuming, let's say, an edge that's contained, or such an edge that's contained in the complement of the Julius set does properly subdivide. And you ask yourself, okay, well, what is that vertex that's in the subdivided complex R of SR? What could it possibly be? Well, it can't be infinity, because it's infinity gets mapped to itself, and if it's this distinct, if it's being properly subdivided, this vertex in the subdivided complex R of SR, is distinct from infinity. So it can't be infinity, because infinity is going to be fixed. And then you exploit this conjugacy to say, okay, well then, if it's in the Fatou set or if this point is in the complement of the Julius set, and in the complement of the Julius set you have this conjugacy, well then, the orbit of this point has to consist of infinitely many points. Your subdivision complex itself can only consist of finitely many vertices, and so that's essentially the idea. So that establishes that you can't have open edges of your subdivision complex be contained in the complement of the Julius set and also properly subdivide. So the takeaway from this lemma is that if you look at, however it is that you might be realizing your map as a subdivision map, if your subdivision complex has edges that are in the complement of the Julius set, then they can only permute among themselves. That's the takeaway, is that they can only, if you have these edges as far as how this map is going to act, they can only permute among themselves. So if we go to the next slide. Okay, so here's, in that example, that original example, I've highlighted the Hubbard tree for this particular Masirovich polynomial z squared plus I, and I'm just reshowing the subdivision complex. I think I meant to have this. I think I originally meant to have this up while I was describing that, but yeah, we can go to the next slide. Okay, so second thing that you want to know is that for a Masirovich polynomial realized by a finite subdivision rule with some subdivision complex S sub R, if you have an open edge that's contained in the subdivision an open edge of the subdivision complex that's contained in the Julius set as opposed to contained in the complement of the Julius set, what can be said? Well, the thing that can be said is that the Hubbard tree must then be completely contained in the one skeleton of the subdivision complex, which is to say, if your subdivision complex is going to include an edge that's in the Julius set, that's completely contained in the Julius set, then you can't get away with doing that without including the Hubbard tree in its entirety as well. So if we move on to the next slide, the proof of that result, this lemma, rests on this proposition that was originally, I guess, attributed to Poirier. I'm not too sure about the pronunciation here, but this result says that let's say you have a finite invariant subset of the Julius set of some Masirovich polynomial. Okay, let's say you say T star of M is the set of closures of components of this convex hull of this finite invariant set minus those points. So you have these components. If in the context of these Masirovich polynomials, you can think of a tree that's been, maybe snipped at each of these points that you're using to define this convex hull. Okay, so if you have a pair of points in the Julius set whose iterates belong to the same element of this collection of closures of components, then those 2 points have to be the same. So if you could say that those two iterates remain in the same component, those 2 points have to be the same point. And so the idea is, okay, so let's say you take the vertices of such an edge that that is contained in the Julia set. And you proceed by contradiction by assuming, let's say you start by assuming all iterates of the vertices of this edge lie on the same side of the critical point, which is to say, can we maybe go back a few slides? I just need a picture of the filled Julia set of this example polynomial z squared plus I. So let's maybe go to can we go maybe up? It should suffice. I mean, go to maybe 20. That picture should suffice. So 25. Yeah, okay, this should suffice. So your critical point, let's say you're looking at the subdivision complex S sub R. This critical point is going to divide this tree into two components. It's just you only have this one finite critical point. It's going to divide this tree into the two components. And if we can go back to slide 27, yeah. So if you assume all the iterates of the vertices lie on the same side of that critical points, which is to say in the same component, you know, given that the critical point divides it into these two, then this proposition by Poirier would imply that the vertices have to coincide, which then contradicts the dendritic nature of the Julia set, because you can't have any loops in a dendrite. And so if then you have some iterate of, you must then have that some iterate of this edge has to contain a critical point. So the iterate of the edge itself under the map has to contain a critical point, and hence the union of the iterates which contain this post-critical set is this closed connected subset of the Julia set containing the post-critical point. And by definition, the convex hull, you know, has a minimality condition, and so by the minimality, the Hubbard tree also being being the convex hull of the post-critical set has to be then contained in the one skeleton. Right? And so that's the idea. Okay, so then sketch of the main result. So just recalling the main result is that we're saying that, you know, our topological entropy, you have this Mazurovich polynomial, you've realized it by a finite subdivision rule. You're looking at the map's restriction to the one skeleton. You want to demonstrate the equivalence to Thurston's original core entropy, which is to say you want to demonstrate the equivalence between the topological entropy of your map's restriction to the one skeleton to the map's restriction to the topological entropy of the map's restriction to the Hubbard tree. So how do you proceed? So you take your one-dimensional, take your one skeleton of your subdivision complex and look and divide it into these two pieces. So you look at its intersection with the Julia set of the polynomial, and you look at the intersection with you look at the closure of its intersection with the complement of the Julia set. So both of these subsets are then closed invariant subsets of the one skeleton. Let's take phi1 and phi2 to be the restrictions to these closed invariant subsets. And then by proposition 1, you have that the topological entropy of the map has to be the map of the maximum of the topological entropies of these two restrictions, right? So then you start by looking at, you start by considering the case in which all open edges are only in the phi2 set, which is to say the complement of the Julia set. In that case, because we know that all these edges can't subdivide and so must only permute among themselves, you look and you demonstrate that the topological entropy has to be 0. So if we look at the next slide, right? Yeah. So in this case, we have that edges are either periodic or pre-periodic. And because we know that the topological entropy is just the log of the spectral radius of the edge recursion matrix, if you look at the edge recursion matrix for a subdivision rule where you just have edges that are permuting among themselves, you'll just get this block diagonal matrix where, you know, each of the blocks are just permutation matrices, right? So since permutation matrices have eigenvalues that are roots of unity, the spectral radius is just 1, and then you'll just have log of 1, which is 0. So if we move to the next slide. Okay, now consider a subspace consisting of the Hubbard tree union with whatever vertices don't end up in the Hubbard tree under iteration. So consider tau to be the restriction to this subset. So we're not including the edges in their entirety, but just the Hubbard tree plus whatever vertices don't get don't end up under iteration in the Hubbard tree. Well, proposition 2 is to tell us that the topological entropy of the maps restriction to this intersection between the subdivision complex and your Julia set is going to be equal to the topological entropy of this map here, which is just the map's restriction to Hubbard tree plus these vertices that don't end up in there. So if we go to the next slide. So a natural way to decompose this subset of Hubbard tree plus vertices that don't end up in the Hubbard tree under iteration is to look at just the subsystem of the Hubbard tree, knowing that it's this invariant subset, and its complement, which is just these vertices, right? So if you further split up this restriction into restrictions into this natural decomposition of y into y and y1 and y2, you call that tau 1 and tau 2. Both of these subsets are closed invariant subsets, right? And so if you once again apply proposition 1, you have that, first of all, tau 1 is just the map's restriction to the Hubbard tree. So as far as the topological entropy of that map, it's just Thurston's core entropy by definition. And then if you look at the complement, it's just the same thing that's going on, because you just have a collection of maybe periodic or pre-periodic points being permuted among themselves. And as far as the topological entropy of that thing, that subsystem, you could determine that it's going to you can analyze it in the same way that you analyze the edges that are just completely contained in the complement of the Julia set. And that essentially demonstrates the result is that this equivalence between the core entropy as we've defined it as the map's restriction to the one skeleton, or the topological entropy of that, and the Thurston's original core entropy, or that the entropy is 0. So I know I'm a little bit short on time, so I'm gonna just move on to briefly describe one slide back. So what this might be used for. This will stay here on 32. Thanks. So there's an operation that enables you to combine a pair of Misiurovich polynomials to yield what's called a mating. So the idea is there's several different there's various mating constructions, but one of the starting points of the most basic ones is called the formal mating. So what you do is you take these two polynomials and you compactify their domains by adding not the 1-point compactification to yield a Riemann sphere, but you take a circle at infinity, adding like a circle's worth of points, infinity times e to the 2 pi it, where t is coming from, you're just parameterizing the circle by r mod z, and you endow these spaces with the topology that makes them closed disks. So now you have two disks corresponding to the domains of these two Misiurovich polynomials. So you take their disjoint union, and identify their circles at infinity in an order reversing fashion, which is to say, take infinity e to the 2 pi it and identify it with infinity e to the 2 pi I minus t of the other domain, and this will induce a map on the quotient space that's referred to as the formal mating. So the map, is essentially just going to be f on the one hemisphere and g on the other hemisphere, right? So if you let's see. So if you so the Mandelbrot set being a closed compact connected full set gives you these external rays, and this is one way by which to parameterize these polynomials. Is you look at their landing points for rational arguments of these external rays. So one way to denote Misirovich polynomials under this parameterization would be to just have f subscript the angle that corresponds to that parameter, to the ray which lands on that parameter in the Mandelbrot set. So so if we go to the next slide, here would be a picture. I mean, maybe ignore the rays for the moment, of the formal mating of the polynomial f1/4 with itself. So if you were to take the external ray with argument 1/4, look at the parameter that lands on, take that polynomial and mate it with itself in accordance with the construction outlined above, you'll have this domain. If so, you can realize these. I think we should go maybe to the next slide. Yeah. So additionally, you can define an equivalence relation on the domain of the formal mating by letting the external rays of by having every external ray with their landing points comprise an equivalence class. So you intuitively you can think of this as gluing the filled Julia sets of these polynomials along their boundaries together, and the induced map on this quotient space, when you perform this identification, is referred to as the topological mating. So there are this construction isn't always going to yield a nice map, and essentially these obstructions to having this construction work out for you is that the equivalence relation might not be closed, and the quotient space might not be a sphere. I mean, imagine taking two Misirovich polynomials whose filled Julia sets are dendrites and gluing them together. You want a map that is, something that is like a rational map, and it's hard maybe to picture two dendrites being glued together to yield the domain that would be like equivalent to a sphere, which in some cases it works out, but in some cases it doesn't. So if we move on to the next slide. One last form of mating is called the degenerate mating. So instead of topological mating is kind of having you identify along all these external rays, which if you're intuitively thinking about that as gluing, these two filled Julia sets along their boundaries in its entirety, you could kind of go halfway between this formal mating in which you're not making any identifications and this topological mating where you're making identifications along all these points along the boundary. You can go kind of halfway and only identify certain points. And you could try your best to make identifications so as to maybe still preserve certain mapping behavior, but at any rate, so there's a result from one of my advisor's former students, Mary Wilkerson, that finds constructions for finds ways of realizing these matings, these maps, these matings between polynomials by finite subdivision rules. So for a large class of formal and degenerate matings, Wilkerson's work realizes these maps by finite subdivision rules. Well, now we have like a conception of entropy for maps that are realized by finite subdivision rules, and so the natural thing is to turn your attention towards these maps and what entropy what you could say in this setting, right? So if we go to the next slide, and the result is something pretty nice, which is, let's say you have two Misirovich polynomials f and g. Let's say you realize the formal mating. Let's say you realize the matings under one of these constructions developed by Wilkerson to realize these matings by finite subdivision rules. Say h of f and h of g are Thurston's core entropy for these two Misirovich polynomials. A result demonstrated in my dissertation is that the topological entropy of this, of these finite subdivision rules, which is to say, take the subdivision maps restriction to the one skeleton in these settings. It's just going to be the maximum of the Thurston's core entropy of these two Misirovich polynomials. And more or less, that result is obtained by judiciously labeling the edges of your subdivision complex, and that arises in these constructions developed by Wilkerson. So I think that's all. That's it. I'll just stop for questions now. Thank you for allowing me to speak.
All right. Thank you, Daniel. Was very interesting. Yeah, we're a little bit out of time. So yeah, there's some questions. So that will be, I mean, if there's any question will be directly